Cool. So next let's look at a variant of this cascode, right? And again we'll start with the single-ended version and then we'll construct the differential. So in the telescopic cascode we had an NMOS transistor to which we applied the small signal, let us say delta V or whatever, and this converted the voltage to a current, and this current was buffered by an NMOS common gate, and at the top we had a cascode current source using PMOS, and then we did this, right? Again, incrementally gates are all shorted. So now if you see here, okay, and before that, this portion, remember, it's just acting like a current source. Okay. Now if you look at this, what kind of configuration have we put this transistor in? You know, 3 configurations, right? Common source, and what is this guy operating in? Common gate, right? So again, if I were to say, cascode is basically a combination where you have a common source followed by a common gate. That's all. And in this case I have realized common source using an NMOS and the common gate also using an NMOS. Now just like you can realize a common gate with an NMOS, we can also implement common gate with PMOS. So that will give another combination where you can have this to be NMOS and this to be PMOS. That's also fine. Okay. And again, you can have other 2 combinations also, wherein this could be PMOS and this could be NMOS and both PMOS. Right? So we look at this case where common source is of one variant, common gate is of the other variant. Again, as of now, there seems to be no real motivation to do this, but that's okay. I mean, most of the times in research or even in real life, that's what happens. You see something, you try it out, see if it's good or not, and then decide, right? So let's try that. So to remind you, remember for a PMOS transistor in common gate, the input current is supplied to the source, output current is taken at the drain. Same with the PMOS, input current is supplied at the source, output current is taken from the drain. Okay. So now I plan to make a cascode wherein I'll highlight it so that the common source is of NMOS, but the common gate I'll realize using PMOS. Okay. So let's quickly try and do that. So I have common source NMOS. Next I want to have PMOS common gate. Right. So basically I have to take the current, feed it to the source, so which means this current has to feed here. So incrementally I just need this path, right? That's all. Okay. And the output is taken from the drain, so here is where I'll take the output. This is the core, and here I had a cascode current mirror with the PMOS. So what do you think should come here? NMOS cascode, sorry, not current mirror, current source. Cascode current source is what was used here. So here also I will have a current source realized using a cascode but with NMOS. So again, incrementally I'll draw it like this. We'll see the final picture. So again, if I label the transistors this way, what is the small signal gain here? Which transistor is providing the transconductance? So short circuit GM, if you find, it's going to be minus GM2. What is the output resistance? Looking down, you have what? An NMOS cascode. Looking up, what do you have? It is still a cascode, right? Remember, the only difference is the common gate is now of different variant than the common source. That's all, right? Please remember, with respect to small signal, there is no difference in using an NMOS transistor or a PMOS transistor. Okay. So whatever you calculated for the old cascode is going to be same. So what is the output resistance? Looking down, what is the resistance? Similarly, what is the resistance looking up? That's all. This is a cascode transistor. So GM4 R0 4 times R0 2. So this is how we want with respect to small signals, but of course let's make the full thing. So all of these will be connected to appropriate bias voltages. I'll just mark it. You can figure out how to generate these later. So here also with some VB. Okay. And of course I also will have a supply. Incrementally I should have this portion to be open, but with respect to the operating point I should be drawing current from the supply, right? Current has to flow from there only. So what will I put here? Current source, because incrementally this has to be open, but with respect to a DC operating point I need something to establish current flow in these two branches. So I will have a current source here. Okay, this fine. So that's the only difference we'll have between these two. Okay. And what kind of transistor do you think we'll use to realize this current source? Why not NMOS? Sorry, someone was saying something. I mean, this current source I can realize both using an NMOS or a PMOS. Which might be a better option here? Why not NMOS? That's the question. Yeah, I'm sure you understand. So if I put the current source like this, I want the impedance looking up to be really large, but if I have an NMOS, it's going to be small. So PMOS will be the right choice. So this is not good. So anytime you come up with something new, you have to name the circuit, and this is called the folded cascode. At least logically makes sense why the name came about. So yeah, only difference is here the current is kind of folded into another branch to generate the final voltage. Okay. So this is the single ended. Let's quickly draw the differential and then do all the calculations again. So what I'll do, I'll put it to the side so that it's there for your reference. Let's draw the differential. So I'll have an NMOS differential pair. Same thing, no change here. Okay. Now this NMOS transistor is generating the current and giving it to a PMOS common gate. So I'll have a PMOS common gate. So basically, let's say one of them feeds here. Done. And output is taken from one side. Let us say output is taken from here. Okay. And at the bottom I have a cascode current source. So I'll put a cascode current source here. Okay. Is it okay? I've taken the same thing and drawing it. I'm drawing two halves of it and just put a tail current source here. Right? And of course, we need to have a current source at the top for each branch. So we'll have current source for this guy.
Bottom current will be divided, then why we require the extra current from above. The bottom current will be divided.
No, but see, where is the current flowing from? It has to come from the supply, right? Okay. I mean, current is not coming from thin air, no? Supply is, I mean, it's all flowing in a closed path. Remember that this is going to be a voltage supply like this. Current is flowing in closed path. Okay. Is this okay? Right? So let's say I call this as I naught as usual. Sorry, which current source? Okay, so why are we having this current source actually? I mean, and that was doing something else also. I mean, I could also do this. But why did we? I mean, you could have a differential amplifier also like this, right? Why don't we do this? And why do we do this? Remember that your circuit has to respond only to differential signals and not common mode. If you recollect, in the common mode response, we saw this tail current source is what was providing that common mode rejection. If you don't have it, it is going to respond. I mean, if you do it like this, right? Let us say I have a differential amplifier like this. Okay, I've drawn it very badly, but okay, right? Even if both of them change by the same factor, both outputs are going to change. But we don't want that. We don't want our amplifier to respond to common mode changes. We want it to respond only to differential mode excitation. And the current source here will help you in that. So please go and check the calculations we did for the common mode response. So there we would have found that only if we have an infinite resistance looking down, the amplifier rejects any common mode changes. Okay, so now finally let's also convert it to a single-ended output. So which means I have to do some kind of diode connection here. What can I do? Or before that, let me label transistors. M1, let's say M2, M3, M4. So how can I bias this now? Where can I make the diode connection? Gate of? Drain of M? Okay, yeah. This, right? So we can do the high swing cascode current mirror. We can also do this connection as we saw, but that will have a smaller swing. Okay. Cool. So let's erase this. This is not needed now. Okay, so let us say I want this branch to be biased at a current I1. Okay, both the branches here. So what should be the value of the current source here? Okay, current flowing here is I1. Here it is I0 by 2. So total current is of course we'll see which of the two currents has to be higher and so on later, but as of now it can be anything. Let it be like this. So let me mark it here. Cool. So again, if you find the small signal gain, do you think it will be different from the telescopic cascode or same as a telescopic cascode? Why? Same, right? So again, with respect to small signal, this is going to have the same small signal equivalent as the telescopic cascode we saw. So the small signal gain is going to be exactly same. Okay. So, but I will not do that. So you take it as an exercise and work out GM, R out, everything, so that you get some practice. Right. So only thing that will change is DC operating points and large signal behavior. So let's briefly look at that. Yeah, so first of all, if I call it VD5 and VD6, what is VD5 and VD6? VGS of M7 at what current? I1. Right? Okay, let me also mark the bias voltages. This has to be VB4. Similarly, what can you say about these voltages if I call VD, this is 2 or 1, yeah, okay, VD1, VD2. VD1 and VD2, what can you say about those two voltages? What is setting them? No, what is setting that value exactly? It's VB4. Remember that this is something that you are going to apply. We are going to have a fixed source to gate drop across the transistor because current is fixed. So what is this voltage? Can you tell me? VB4, yeah, plus VSG of M4 at a current of 5. Cool. So this is this. So then let's find the same two things again, common mode range and slew rate. Let's do common mode range because that might be shorter to do. Let me copy paste this. Okay, let's quickly tell me, we have done this before. So again, for common mode range, I'll assume that I'm applying the same input to the two gates. Let me also replace all these guys with transistors. So here I have M0. Or let the currents be there. So here I replace the current source with a PMOS transistor M9 M10. Okay, so now can you quickly tell me, if I keep reducing the input common mode here, which transistor can go out of saturation? M? Oh, sorry, it's not M6. It's okay. My 6 and 0 are looking similar. 0. Okay, M0. So what is the minimum the input can go? It is the gate to source voltage we have to maintain plus the overdrive. The gate to source voltage of M2 is fixed, so that is fixed, plus the minimum you can accommodate for the drain to source of M0, that is overdrive of 0 at a current I know. Okay. Now similarly, if I keep increasing Vi, which transistor can have issues? M? Yeah, why? Yeah, remember the drain voltage here is fixed. As long as we apply the same gate voltage, the currents are going to get divided equally. So the currents are going to remain same in the two branches. So which means the source to gate here is going to be fixed. So for a given VB4, the drain voltage is also fixed. So the maximum we can go, what is it? Yeah, it can go VD1 plus VTH of, I'll call it 2, okay, VD2 and VTH2. So what is the drain voltage we have written here? I'll just replace it here. This is going to be VB4 plus VGS4 at a current I1. And if I want to make it clear, I will say this is the drain voltage. Okay. One threshold above the drain is what the gate can go, and the drain voltage we know I have directly written. So once again, you note VB4 will have its own ranges of voltages. So if you want to keep maximum for VA, you apply an appropriate maximum for VB4 and do it. Cool. So let's quickly do the output. So I light it here, it's okay. If I keep reducing output, which transistor will have issues? This voltage is dropping, so obviously one of these two transistors will have issues. Which one? M6. What is the minimum the drain can drop? VB6. For an NMOS, the drain can drop one threshold below the gate. That's the minimum. Similarly, if I keep increasing output, which transistor will have issues? M4. What is the maximum it can go? VB4 plus mod VTH4. Right? Maximum the drain can go for a PMOS is one threshold above the gate. That's what it is. Right? So okay, let's quickly find out the absolute maximum and minimum and finish today maybe. Let's see. So let us say now I want to find what is the maximum I can have for the output and minimum I can have. So let's see what is the minimum. What is the minimum VB6 we can have? Or I'll first find out maximum. Let's say what is the maximum I can have for VB4. If I keep increasing VB4, what happens? If this increases, this will keep increasing. So what will happen? Drain voltage of M9, M10 increases. So which means they can go out of saturation. So what is the maximum the drain here can go to? Right? So the drain can go, I'll write VD2 max is the supply minus the overdrive of M10 at a current of I0 by 2 plus I1. That is the maximum this guy can go. So which means what is VB4? Minus? No. This is the source to gate drop, right? Minus? Is that okay? So okay, then I should put it down. VDD minus overdrive of M10 at a current I0 by 2 plus I1 minus VSG4 at a current of I1. So this is the maximum of VB4. So if I have to find the maximum output, plus VTH4 comes together, this becomes one overdrive. Again, I like it here. So he'll have plus mod VTH4. So that becomes an overdrive. So I can simplify the output max as VDD minus overdrive of M10 at a current this. Again, once again, if you see, it appears that the maximum we can have is supply minus the two drain to source drops, right? VDD minus overdrive of M10 minus overdrive of M4. And again, remember that is possible because we can apply this gate voltage to this value. Okay, because fundamentally the maximum side at the output is limited by VB4. So since we have a free control on VB4, I can maximize it and get this. Okay, can I take 5 more minutes extra? Anyone has a class? Okay, I'll just take 5 minutes so that we can wrap up. So what I'll do is I'll give it as an exercise for you to work out VB6 minimum and Vout minimum. So we have done this for telescopic cascode. Similar will. Okay. So just a couple of points I want to make and we'll wrap up. Cool. So now let us say I'll have these values here. Yeah. So I have the maximum and minimum for the input output, right? So let's say I do the same exercise as I did. I put it in unity feedback now. So again, we have to find what is the absolute maximum and minimum. So how do I find? I have separate limits for the input and the output. At the input I see, the input has this as minimum, output has this as the minimum. If I put it in unity feedback, what should I look at? Higher among these two. And okay, let me go to the circuit here so that it's clear. So one voltage I look is this, right? VGS2 plus overdrive. Other voltage depends on VB6, which is this. Okay. So again, exactly we can't say, but typically, can you comment anything about VB6 and this voltage? Yeah, why?
The minimum VB6 can go is like the overdrive for MOSFET cell plus one gate to source.
Yeah, see, remember that as he's pointing out, VB6 has to accommodate one gate to source voltage plus a drain to source voltage. That is similar to what we have here, right? Again, typically you will find VB6 might be of the same order as this. Okay. Again, you can work out in a way so that it doesn't satisfy, but usually it might be like this. In that case, which of these two is higher? This guy is higher. Convinced? So I'll just put a tick saying that this is the higher. Now similarly for the maximum, I should look at these two, and here it's clear which of this is lower. So we have VB4 plus something. Here it is just VB4 plus a threshold. Which is higher? Sorry, we should look at the lower or the higher here. The lower one is here. So let me quickly write it. The minimum I have, minimum is what? VGS2 at a current I0 by 2 plus overdrive of 0 at a current I0. The maximum I can have in the unity feedback is VB4 plus mod VTH4. And remember that this maximum I have computed to be this. right? If I were to find the maximum of this, I should put maximum of VB4, and I've already computed that here. This is the output maximum, remember. Okay, and the output maximum is already computed here. So I'll write it as VDD minus overdrive of M10. I'll not write the currents for simplicity. I'm skipping the currents so that it's easy now. Okay, so now what is the max minus minimum? I have VDD minus, let us say, overdrive of M10 minus overdrive of M4 minus overdrive of M0 minus VGS2. Okay. Again, if I take the same numbers as before, let us say you have a supply of 1.8 volts with overdrive minimized to 50 millivolts and threshold of around 400 millivolts. What does this evaluate to? I have 1.8 minus 3 overdrive voltages. What is the gate to source voltage? 450 millivolts. So I think around 1.2 volts. Again, just quick calculation. If you recollect, for the telescopic cascode, this came out to be around 0.35 volts, right? So compared to that, you can see there is a significant improvement, and that is exactly one reason why you might want to do this. Use it, this folded cascode instead of the old telescopic cascode. Okay, right? So that is one nice thing. And one more last point. Let's quickly make it so that this is, I'll copy paste this. So here, right, let's say I want to find the maximum I can apply at the input. Okay, VI max, which is this voltage, right? I'll write it here. It's VB4, maximum of VB4 plus VGS4 at a current I1 plus VTH2. I have VB4 max already written here, so let me copy paste that. Oopsie. So this is VB4 max. So in addition, I have VGS4 at a current I1 plus VTH2. Sorry? Oh, sorry, VSG4. Yeah. Okay, fine. I mean, it's okay. It gets cancelled. Okay. It's all VSG4. I made a mistake. Okay. So you'll end up with VDD. I'll again write directly overdrive of M10 without the currents. Okay. And typically, remember, do you think this will be a positive number or a negative number? Positive. Could be typically positive. So basically, the maximum I can apply at the input is. So the nice thing is, the input common mode you can apply at the input here can be equal to the supply itself. Okay. So that is one other feature in applications where you have your expected common mode range for the input is very high, close to the supply. This guy is a good option. So two things are nice in folded cascode. Let me just mark it and finish it. First, when you put in unity feedback, you have better swings. Again, better is in comparison to the telescopic cascode. Secondly, when I use an NMOS input pair, the maximum I can apply at the input can be equal to the supply itself. Okay. Now remember, I can also make a folded cascode with a PMOS input pair. Right. Basically, if I go back here, I made this configuration where the common source was NMOS, common gate was PMOS. I can do the ulta wherein the common source is PMOS, common gate is NMOS. That is also a folded cascode. If I do that, can you comment about the input common mode? What do you think might happen?
The minimum that I can apply can be.
Yeah, again, logically that's what it should be. So VI minimum, you will find it to be equal to 0. Okay. So what I'll stop here. So what you guys do is, before next class, try to draw the circuit with the PMOS input. the same thing, PMOS will be the common source, NMOS will be common gate, and find the minimum input common mode, and you'll find that this can be equal to 0 volts. So these are the two reasons why you might want to use folded cascode, because otherwise you see you are actually having additional current sources here, right? We have one current source here and one more current source here. More transistors are there compared to the telescopic cascode. So it is slightly inefficient. So you might want to use this if you end up in a scenario where you want to use it in unity feedback, or you find that the common mode of your input is close to the supply or to the ground. Okay. So exceeded a lot of time. Let's stop here.